All right, welcome back to the Explainer, math enthusiasts. Today, we're acting as your guides through an absolute masterclass of theoretical physics and higher math. We're going to explore exactly how you mathematically translate the chaotic quantum trace of the universe directly into classical spacetime. So get ready to have your mind benched just a little bit, because we are diving deep into the Adelic Langlands program. Now, this brilliant quote perfectly sets the stakes for what we're getting into today. We aren't just looking at abstract number theory floating in a vacuum here. We are looking at the exact equations where number theory and quantum geometry literally build reality. When these mathematical layers interlock, the Langlands correspondence actually ceases to be just a collection of conjectures. It becomes a dynamical necessity. Because we're tackling some incredibly heavy math today, here is a quick look at our syllabus. We'll be covering 1. The grand architecture, 2. Mapping the canonical bridge, 3. Equations of the geometric bridge, 4. Logos field theory dynamics, 5. Calculating stability and propagation, and finally, 6. The emergence of geometry. Okay, Section 1. The grand architecture. Let's dive right into the blueprint of this overarching theoretical framework. What we have here is a grand, unified framework linking three incredibly complex domains. Spectral projection theory, J-theory, and logos field theory come together to map operator algebras, geometric stability, and quantum field theory directly into arithmetic geometry. And that unification is what forms the Adelic Langlands program. To really wrap our heads around this machine, it helps to process it in three fundamental steps. First, spectral projection theory filters out the chaotic quantum input to isolate specific spectral states. Second, J-theory steps in as the bridge, providing the stability criteria and tracking those states as stable geometric points. And finally, logos field theory generates the actual adelic field dynamics across all local fields. You can see how these specific components stack together into a literal pipeline. You start at the top with the Dirac trace, you filter it, you stabilize the geometric moduli, and then you drive the field equations. The output right at the bottom is our dynamical necessity, completely unifying the spectrum with arithmetic representations. Moving to Section 2, mapping the canonical bridge. Let's establish the translation manual for how these theories communicate. What's really fascinating here is how this acts as a canonical bridge connecting continuous differential geometry directly to discrete arithmetic eigenvalues. We're essentially establishing an exact dictionary over the moduli space of Higgs bundles. Think of it as a literal Rosetta Stone for mathematicians working between Calais geometry and the Langlands program. Let's look closely at this exact dictionary because it's a real game changer. It allows us to unabashedly translate complex J stability straight into the Langlands program. For instance, notice how the J functional maps perfectly to the logarithmic L function action, or how a critical J equation instantly becomes a Hecke eigenvalue equation. We can now take geometric stability conditions and translate them directly into arithmetic bounds. Section 3. Equations of the geometric bridge. With our dictionary established, let's zoom in on the actual input equations. This is where the math just gets incredibly elegant. Look at the denominator in this formula. It shows how Gaussian unitary ensemble, or GUE filtering, acts as this massive statistical averaging process. We're basically taking a wildly fluctuating chaotic quantum operator and passing it through the large and limit. It forces those microscopic degrees of freedom right into a deterministic hydrodynamic limit. So out of quantum chaos comes perfect order. Breaking down the essential variables of that setup, we have the topological constraint, which is your external stabilizing potential. Then we subtract the geometric coupling, representing the microscopic interaction with the reference metric. But the key is that logarithmic repulsion term. It acts energetically just like the localized pressure of an eigenvalue fluid, functioning as a crucial spatial stabilizer. And that balance gives us the critical J equation. By taking that eigenvalue pressure and balancing it squarely against the arithmetic background potential, we find this beautiful equilibrium. The global topological invariant minus the reference metric over the spatial volume element mathematically equals 0. Now, if your head is spinning a bit with the math, don't worry. The absolutely crucial takeaway here is the semi-classical insight. Classical geometry is entirely derived from quantum microscopic fluctuations. The critical J equation isn't just assumed or postulated. It actually emerges as a macroscopic equation of state. Those quantum microstates transition into a mean field equilibrium to create a stable geometric reality. All right, Section 4, Logos Field Theory Dynamics. Let's see what happens when we activate these fields. Take a look at this action functional. It beautifully splits the geometry. we have the continuous Archimedean places, the smooth geometry, integrated with the discrete non-Archimedean Broussard-Tits trees, the arithmetic geometry. And they are bound together tightly by this logos core, which is an interaction term enforcing strict global reciprocity. By applying the variational principle to that action, setting it to 0, we get a fascinating split system of local equations. For the Archimedean smooth places, we get the nonlinear J-Laplacian for spatial diffusion. But for the discrete non-Archimedean places, we get a discrete Hecke difference equation. Think about that. Two completely different types of math, entirely generated by one unified field. But they cannot exist in isolation. This equation proves they are bound globally by what's called the Adelic interlocking condition. The non-Archimedean component basically acts as an arithmetic clock, stepping the field through the prime spectrum. And the whole shebang is bound by the completed Dedekind zeta function, acting as a global, non-local scaling operator. An arithmetic clock ticking through the prime spectrum, it's just conceptually beautiful. Section 5. Calculating stability and propagation. Let's figure out exactly where this highly complex structure might destabilize mathematically. Notice the explicit cyclic p-adic Fataki invariant equation here. This measures the exact mathematical threshold of stability. Look at the local ramification index in the exponents. If that ramification gets too high, the second term overwhelms the first. The invariant flips negative, causing literal geometric instability. And what's wild is this perfectly matches a sign change in the local Langlands root number. Finally, Section 6, the emergence of geometry. This is the climax of our masterclass, where we mathematically prove how physical space-time emerges. Look closely at this incredible equation. We are seeing the Gillet-Soulé-Arakelov metric emerging as the classical stress-energy tensor, the smooth spatial curvature, the Ricci tensor, and the discrete arithmetic pressure from the Hecke eigenvalues. They unite. Together, they form the exact stress-energy tensor of gravity. Space-time curvature traced directly back to the localized density of the logos field. Gravity is literally born from arithmetic. And the physical consequence of this math? It's geodesic scattering. Look at the deflection angle equation. Highly ramified local conductors, which are those arithmetic singularities, they actually act as gravitational lenses. They carve out conical deficit angles that physically deflect the straight-line, classical paths of geodesics. Arithmetic is directly bending spacetime. This entire mathematical framework proves that classical geometry isn't just an arbitrary backdrop. It's dynamically carved out by the stress energy of an underlying adelic field decohering into our universe. And it leaves us with a pretty profound mystery to ponder. If gravity and geometry are merely the macroscopic echoes of number theory, what other incredible physical secrets are hiding in the prime spectrum?